You know, it's pretty wild when you stop and think about it. There are these invisible rules that run our entire physical world. Everything, from the weight of the stuff you buy at the store to the time on your phone, it all depends on this shared language of measurement. Today, we're going to pull back the curtain and look at the architecture behind it all.
So, let me ask you something super simple. What's your height? Just think about it for a second. Some of you probably have an answer in feet and inches, right? Others might be thinking in centimeters.
And here's the thing. Both of those answers, whether you said 5'8" or 173 centimeters, they're both totally 100% correct. So how is that possible? How can two completely different numbers describe the exact same thing?
Nope, it's not a trick question. The answer actually gets at a really crucial difference in how we measure the world. And it's a difference that's fundamental to, well, pretty much everything. Science, engineering, even just buying stuff from another country.
And it all comes down to two key ideas: dimension and unit. The easiest way to think about it is like this. It's the difference between what you're measuring and how you're measuring it.
All right, first up, dimension. A dimension is just the big fundamental idea you're trying to measure. You know, a basic property of a thing. We're talking about concepts like length, mass, time, or temperature. These are the abstract whats.
And then you have the unit. A unit is the specific label we stick on that dimension. It's the language we use to actually talk about it. So for the dimension of length, our units could be feet or meters. For mass, it could be kilograms or pounds. Units are the hows.
Okay, so let's circle back to that first question. Your height's dimension is length. That's the core concept. The units you use to talk about it, feet, inches, centimeters, that's just the language. See? Same dimension, just different units. And once you get this difference, it unlocks this sort of golden rule that runs all of physical science. It's a rule you actually already know, even if you've never really put a name to it.
We've all heard this, right? You can't add apples and oranges. If you have 10 apples and 10 oranges, you don't have 20 of anything. You just have 10 apples and 10 oranges. This super simple idea is the absolute key.
In the world of science and engineering, this means you can't just add or subtract things that have different dimensions. An equation like 8 kilograms plus 3 feet? It's completely meaningless. It's just nonsense.
And why is that? Well, because kilograms measure the dimension of mass. Feet measure the dimension of length. They're as different as a donkey and a horse. They're just fundamentally different things, so you can't mush them together.
But, and this is the really cool part, you can do the math if the dimensions are the same, even if the units are different. 8 kilograms plus 3 pounds? That's a totally valid calculation. Why? Because both kilograms and pounds are units of the exact same dimension, mass. You just have to do a quick conversion first.
Now, this all seems pretty straightforward to us today, right? Well, for most of human history, the world of measurement was pure chaos. I mean, just imagine trying to build a global economy when a pound in one town was different from a pound in the next. It was a mess.
Before the middle of the 20th century, all these different empires and colonies and regions had their own separate, unique systems. It was like they were all these little isolated islands, each speaking a totally different language of units. And that made doing science and trade incredibly difficult.
So you ended up with this messy competition. You had the CGS system, which was all about the centimeter, gram, and second. Then there was the MKS system, using the meter, kilogram, and second. And of course, the FPS system, which was big in the British colonies, using the foot, pound, and second. Total confusion.
But out of all that chaos, a new order started to emerge. The world finally realized it needed a single, unified language of measurement if we were ever going to move forward together.
The big push, the thing that really forced everyone's hand, was World War II. The explosion in global cooperation and, let's be honest, international trade made a standardized system an absolute must-have. You just can't build a global economy on measurement confusion.
And the solution was the System International, or as we all know it, the SI system. This became the modern global standard, a universal language of measurement that today underpins basically every part of our modern world.
Okay, so we have this global standard, but that kind of brings up an even deeper question. What is a kilogram? Like, for real, where do these official definitions actually come from? And the answers, well, they are genuinely astonishing.
You're not going to believe this, but for over 100 years, the official standard for 1 kilogram was literally this one thing: a small cylinder made of platinum and iridium that was locked in a vault in France.
The mass of the entire planet was based on this single physical object.
But today, oh man, it is so much cooler. We don't rely on physical objects anymore. We rely on the fundamental constants of the universe itself. A meter isn't a metal stick anymore. It's now defined by the speed of light. It's the distance light zips through a vacuum in a teeny tiny fraction of a second. It's a standard that would be the same here, on Mars, or in some galaxy far, far away.
And what about time? Get ready for this. A modern second is defined by the wobble of a cesium atom. We're talking about counting over 9 billion little energy wiggles inside that atom just to mark off a single second. It's this incredibly precise, unblinking cosmic heartbeat that makes all our modern tech, from GPS to the internet, even possible.
This precision gets into some pretty deep stuff, like chemistry. Ever heard of a mole? It's basically a chemist's version of a dozen, just for counting a gigantic number of atoms. And the standard elegantly connects the tiny atomic world to our world. It just says that the mass of 1 mole of something in grams is the same as its molecular weight. Simple, but powerful.
So we've gone from this total chaos of local customs to these beautiful, universal standards that are literally woven into the fabric of nature. And it makes you wonder, right? Now that we've standardized how we measure the physical world, what's the next big human idea that desperately needs a global standard?